Namaste. We're about to understand a very important concepts under the fluid mechanics called Newton's law of viscosity. The prerequisite is the definition of viscosity or a bit of understanding related to a thing called viscosity. So viscosity is kind of a force, is a cohesion force between two layers, and viscosity is a measure which says that how thick or thin is the fluid is. Let's just assume a flow through pipe. The flow is called discharge or volume rate. This is the flow. Now there are two sections which can be considered. This is the cross section across the direction of flow, and the diameter of the pipe is d. At the same time, along the flow, we can also take a section, and that is called cross section or longitudinal section, rather, which is of prime importance here. The longitudinal section will tell you the way in which the water is moving, or rather, it tells you something related to the velocity. Now, we just go into some depth regarding the longitudinal section of flow through pipes. So this was the cylindrical pipe, or so-called the longitudinal section in a sense of section. Now at a point, if I can draw the velocity profile, how velocity is varying, it is evident that at the boundary peripheral points, due to the surface roughness, velocity is almost nil or it is equals to zero. Velocity can be neglected on the peripheral points, and velocity goes on increases. As it comes to the center line, it attains a maximum value. So some amount of velocity, some more amount, and when it comes to a center line, it gets the maximum velocity. Now when I join all these points, actually I get a velocity profile, and this would be the velocity profile where maximum velocity is always expected at the center line, near the center line. Okay, now this flow can also be visualized in terms of sheets of paper. So this is how we can visualize the same flow. So let's just assume that the flow is discretized with the help of sheets of papers, except the fact is the velocity is represented here. Now the maximum velocity, or let's say at the center line, you measure a velocity and that velocity is maximum velocity. Other than the center line measurements of velocities, other than that, we get a minimum velocity, or the velocity would be less than this maximum velocity. Now, if I just try to draw the fashion with which the velocity is varying, so this is the velocity u, and on the other layer, it is slightly more. So, how do we quantify that slightness? It is in terms of du, and these two layers are separated at a distance called dy, a very microscopic distance, that is dy. Okay, now my aim is to draw all these variations in a graph of y is nothing but the y direction, the depth or diameter along its longitudinal length. So there exists some cohesion forces between the layers here. At a time we consider u and u plus du. The layer u will exert some force on u plus du layer, and subsequently u plus du will also exert some amount of cohesive force on u layer. So ultimately, there is a force which is created, which we call it as shearing force, and the stress force divided by area, the intensity factor, the stress created due to this cohesive forces called shear stress. So we'll exaggerate this portion now. So we just try to draw the profile. The profile is almost similar to what we have seen here, the velocity profile. We just consider two layers here. So the direction y in the ordinate and two layers. This layer is du plus u, and the other one is just u, and this difference is the distance is dy, the width is dy. So this is how one can expect minimum value of velocity at the periphery, maximum somewhere here at the center line. Okay, so this velocity is u plus du, that slightness is du here, and dy. Yes, so at this point we can define something called velocity gradient, or which is also called uh, the rate of shear strain. Velocity gradient is u plus du minus u, difference in velocity in y direction, that is dy. U plus du minus u divided by dy. U and minus u, they get cancelled, and du by dy is the velocity gradient, or the same is coined as the rate of shear strain. So u and u plus du, they will exert a kind of a force, and then we call it as a shear stress, and it is due to that shear stress, and there is a velocity gradient. We can say shear stress is directly proportional to du by dy. Du by dy is velocity gradient, or it is also called uh, the rate of shear strain. So tau is proportional to, now I would like to replace that proportional to sign by equal. So tau is equals to a constant, or a proportionality constant, a coefficient, into du by dy. Now this coefficient is called as viscosity, and further we call mu as the dynamic viscosity. So here we try to define a very important principle, which is known as a law, Newton's law of viscosity. We derive it with the help of this tau equals to mu into du by dy. Tau equals to mu into du by dy, where mu is a proportionality constant, and we call it as viscosity or dynamic viscosity. The Newton's law of viscosity is defined with the help of shear stress tau, rate of shear strain du by dy, and the dynamic viscosity as the shear stress is directly proportional to the rate of shear strain. We can also replace the rate of shear strain with the help of velocity gradient. It is also true. And the constant of proportionality here is coefficient of viscosity, and the liquids or the fluids which obey the rule of tau equals to mu into du by dy, or the fluids where tau divided by du by dy is equals to mu, are called Newtonian fluids. The fluids which obey Newton's law of viscosity are called as Newton's or Newtonian fluids. Thank you.